The Tokamak. Is it possible to be the future of energy? Let's dive deep into the specifics of what a tokamak actually is. So protons are positively charged. They repel each other due to the electromagnetic forces for fusion to happen. The nuclei must come close enough to overcome this electromagnetic repulsion and allow the strong nuclear forces to take effect. However, getting the nuclei close enough for fusion is challenging due to the Coulomb barrier, the electrostatic repulsion. This is what is needed for fusion to take place, the combining of atoms. To solve the Coulomb barrier problem, fusion requires extremely high temperatures and energy. At high temperatures, the nuclei move with high kinetic energy, increasing the chances of them getting close enough for the strong nuclear forces to bind them. The more energy the nuclei have, the faster they buzz around, which makes it easier for fusion to take place. Deuterium and tritium are isotopes of hydrogen. These isotopes are used as the fuel for the nuclear reaction because it reaches the best outcomes at the lowest temperatures and release more energy than other elements. It is also easier to join the atoms as positively charged protons in the nuclei repel each other due to the electrostatic forces. In fusion experiments and reactor experiments, the plasma is heated to extremely high temperatures, around millions of degrees Celsius. At this temperature, the gas becomes a plasma. Well, what is plasma? Well, you get solids, liquids, gases, and next is plasma. Plasma is where electrons are stripped away from the nuclei, creating a mixture of ions and electrons. A mixture of both deuterium and tritium will be added to the vacuum chamber, which is ionized, and heated to the thermonuclear temperatures. Then these fuel particles collide with new fuel particles, which gives us a sustaining fusion reactor. In fusion, two light atomic nuclei come together to form a heavy nucleus. When they combine, they release a large amount of electricity, energy, which is turned into electricity in this process. So if we look at the tokamak from inside, you have many different layers, which we also call many different walls. The most important wall is the first wall. It is called the limiter, as it is the first boundary for the hot plasma. The basic requirements of the limiter is to withstand the intense heat and particle fluxes falling on it without severe damage. The limiter must also protect the vessel wall and other systems inside the chamber from damage. The limiter material must also not generate significant impurities by thermal or particle inducers, desorption or sputtering, and must have good thermal conductivity for heat transfer. The blanket is the second layer, or the second wall in the tokamak, which has three layers within itself. The first layer is a region of neutron multiplication. The second layer is where the fast-flowing neutrons get slowed down, and the third layer within the blanket is where the tritium is produced. Next is the earlier conversion layer, which is where we get the heat, which is used to boil water, which turn turbines and then create electricity. Then we have the shield that stops the final bit of plasma if anything does escape, and then after that the vacuum vessel follows. This process stops the plasma from getting outside of the vessel, but also keeping the plasma at its temperature that works best for the fusion to take place. So how do we know what is actually happening inside the tokamak? What do we use to measure? So there is the Rogowski loops, which is a toroid of wire to measure the plasma current. Diamagnetic loops and internal magnetic pickup coils to record the shape and position of the plasma. Radiometers measure emissions and different frequencies, while infrared monitors are used for plasma density measurements. Soft X-ray emissions by plasma yield measurements of plasma temperature, while the hard X-rays give information on energetic electron tails and runaway electrons. There are infrared cameras which are used to monitor the limiter surface temperatures. These are only just a few of what is used to measure the tokamak and the fusion process that happens inside. So, is there any waste produced? Yes, there is. Activation at high energy neutrons can also create radioactive waste, which is a problem, but we can control this a lot better instead of releasing carbon dioxide into the air. But this radioactive waste is only created in very low quantities compared to fission energy. So is it the future of energy? After doing this deep research into the topic of fusion energy, I definitely feel like fusion is the way forward. With a minimum amount of waste being produced and creating a large amount of potential energy, there's very small amount of waste that will get produced and it won't contribute to global warming. We do have challenges that we need to overcome, but we are constantly getting closer to the break-even point and getting past these challenges. With the amount of money and resources being used to try and achieve the break-even point, I think we'll reach it by 2030. This will only happen if we keep on putting the resources and effort, which we are. We need more people to help out than ever before, as we are reaching a time where cancer or poverty is not a problem, but climate change is. As if we don't solve climate change, there'll be no humans. So yes, we have the future of clean energy. Fusion is potentially here. So let's keep on striving for greatness. Hope you enjoyed watching this video and got a little bit more insight into fusion energy. If you would like to, check out my article which I wrote on this, which has a little bit more information and goes into a little bit more depth. But anyway, thanks for watching.